I give you now FX with the Blitzableiter release.
Thank you. Hello. I don't see anyone. It's way too bright here. Okay, so this is the release of our tool Blitzableiter, which we worked on for about a year now. So what is this about? Oh, great, my slides don't advance on the screen. This is excellent. So essentially, this is a defense talk, and this is a defense tool. So I wanted to start off with saying that security is actually trying to make shit happen a little bit less often. So nobody is going to provide you perfect defense with anything, and not even like things that come in yellow boxes are going to protect you from everything. But this tool is meant to actually provide a additional layer of protection when you deal with flash content. So what are we going to talk about today? The motivation behind the tool, the attack surface that we look at with flash, who's actually victim of attacks that use flash as a vehicle, and what options do we have. Then I'm going to show you fairly early what the tool can do for you, so you can leave the room and watch Dino's talk or something. And for everyone else, we're going to go into the gory details of flash internals and how this makes writing such a tool a little bit more challenging than we first thought. So the motivation behind this is there was a project in 2008, late 2008, that we participated in that looked at rich internet application platforms and their security, and essentially it turned out that Flash sucked a lot more than everything else. And we tried to figure out like what can be done about it, and how can we possibly secure Flash without firing everyone at Adobe. Essentially it turned out that the Flash runtime, like the Flash player itself, is essentially unfixable, at least for third parties. I don't know how Adobe looks at that. And the traditional detection mechanisms essentially fail pretty badly. I'm going to go into details there later. And we constantly see new Flash exploits surfacing that essentially pwn your browser. And we didn't want to write yet another antivirus type of tool, so we wanted something that is signature free and that can be written initially and then tested and debugged and stuff, and then at some point you're done and the tool actually does what it is supposed to do without constant updating. So what's the attack surface we're looking at? The Flash files that you load into your Flash player are actually a container format. They contain a lot of stuff, vector graphics, pixel graphics, fonts, sound, video, and virtual machine bytecode for the Adobe virtual machines. You can already see that this is a lot of stuff to parse. And the data structures they use for that are heavily version dependent. They're backward compatible until like back to the first version of the file format specification. The parser is written in unmanaged language in C or C++ or whatever they use over at Adobe. And yeah, essentially it's very, very fragile. 90% of this Flash player is parser code that you can attack. So what type of victims do we have? First of all, well, we get owned when we serve porn. That's the most pressing problem with Flash is, the porn comes in Flash. And so you commonly get exploited with things like the CVE 2007-0071, which, by the way, if you haven't read the paper on from Mark Dowd on how he exploited that, I highly recommend it. It's very good, very well written, and interesting research. And so what happens is you load a Flash file in your browser and it yields code execution essentially. But we also have DNS rebinding attacks that use Flash. Dan Kaminsky made use of Flash for DNS rebinding a couple of years back. You can do CSRF type attacks. You can use Flash to create HTTP requests that open via UPnP, open ports in your home router or stuff. And some exploit toolkits actually leverage the fact that Flash has access to many version informations on your actual host. And so, what the hell? Yes, please go on. And so that's also something that Flash is used for, just as a front-end vehicle for exploit toolkits. 97% of all web browsers report Flash to be installed, and there is a quote from someone that wanted to remain anonymous, and he said, telling people not to use Flash is like telling them to not smoke. It just simply doesn't work. So, as an end user, if you want to protect yourself against those Flash attacks, what are your requirements? First of all, most of the attacks are, or pretty much all of the attacks, are based on a somewhat malformed Flash content file that then, when it is parsed, will actually, trigger an integer overflow or buffer overflow or that type of memory corruption. So the end user essentially needs a way to verify that the file is well formed. And technically, that's something that the Flash player should do, but that's exactly the problem. It doesn't. And so we have to provide that as an additional functionality, and we preferably want to have that in your web browser. Also, what's important for end users is that the porn actually loads quickly. So you don't actually wait half an hour before you see the naked girls or whatever you go off for. Performance is an issue for the end user. There's a second class of Flash attack victims that is not so apparent, but it's an actual big problem, which is website owners and especially advertisement networks. Whoever invented beer, great. So what happens is, often in the ad networks, so they receive the content, the banner content, in pre-compiled format. So it is already a Swift file, and they have pretty much no way to check it. So often they have teams that would load up the banner and look for inappropriate content or stuff. But then when the banner is actually put online, it will go to some third-party server and report that it's now in the ad network, and then it will change behavior. I mean, you have code within Flash, so you can easily program that type of functionality. A couple of large news media sites, like the New York Times and a couple of German sites, have been hit with Flash banners that actually serve malware or scareware to the users. And this is not only very embarrassing, it's also when it's not serving malware, but it's actually forwarding the user to different sites for a click fraud or something. It's actually very damaging for the sites to do. So they have different requirements. Ensuring the well-formedness of the file format is only half the deal for ad networks. It does help preventing the people that look at the banners from getting owned, but that's not all. What they actually want is to enforce the contractual requirements that they put out, like for any given advertisement campaign, there's only one target URL, and you're not supposed to forward the user to a different target URL. And this is something they want to enforce or verify within the actual code in the Flash file. So those operations are computationally more expensive, but it's actually less of a concern because it's running server-side and it's actually executed when the Flash content is uploaded. So it's not something that, that happens all the time, but only when you receive the Flash file. So, sorry, I couldn't resist. So what Flash actually natively provides in terms of security is very limited. So you have a couple of settings that you can do on so-called I don't know what it is, settings manager, right? Which is actually a Flash file hosted on macromedia.com, and I don't even want to know how they did that. So you can turn on and off like access to your camera or your microphone and stuff, but it's very, very limited. There is a lot more settings that you can do in a not very well known configuration file called mms.cfg, very obvious name, where you can actually like prohibit uploading files or downloading files via Flash and stuff. The next thing is Flash doesn't have any proof of origin, so there's no such thing as signed Flash files. Although they support pretty much every stupid video format and sound format on the planet, they don't have a signature mechanism. I said initially that AV and traditional detection methods are pretty much a bad fail here. And here's an example. So Gnida is one of the most common pieces of Flash malware that actually uses Flash functionality. It's a click fraud, banner campaign piece of code. And when you feed it to VirusTotal, you get about like 70% coverage, which is already pretty bad. The interesting thing is Flash files are internally usually compressed using zlib. Like nothing special, no fancy algorithm, it's just zip essentially. So if you go ahead and decompress the Flash file, it's still entirely the same byte content, it's just decompressed, and you feed it to VirusTotal again. Your coverage drops from 70% to 20%. Which means that they're actually matching on the compressed data. That's stupid. But it's, given the amount of samples that AV companies have to deal with, nobody actually looks at samples unless they're really interesting and exploit like Siemens SCADA networks. So that's the reason why AV doesn't help us here at all. So our alternative defense approach, Blitzableiter, comes as a straight command line utility. So you just feed it a Flash file that is potentially malicious as input. If it's grossly malformatted, it's rejected right away because we can't make any sense of it. And otherwise, it produces a hopefully non-malicious Flash file as output. As simple as that. If the Flash file was well-formed and you know it was good porn, then the result should actually be functionally equivalent to what you put into it. Yeah, the word Blitzableiter is the German term for lightning rod, since what we're trying to do is turn dangerous lightning into harmless Flash. The thing is implemented in C# and targeted on the .NET 2.0 runtime, so it runs nicely on Windows and Mono. If you are on OS X, that's your problem. So how do we get this into the browser? I asked Giorgio Maone to what he thought about this idea, and he actually created support for external filters, generic external filters that includes Blitzableiter, but you can also use your AV into NoScript. So if you're on Firefox and you have NoScript, then it's very easily integrated. It's MIME type based, so you just give it the Flash MIME types, and it will then run Blitzableiter for every piece of Flash that you want to look at. it actually required some serious design and code changes to do the background processing. And the current NoScript versions actually already support external filters. At this point, I would really like to thank Giorgio, because normally if you try to work with someone else and suggest that they change their stuff so it supports your stuff, it takes quite a lot of convincing or throwing money at it. In this case, he was really responsive. He was right up to the idea and invested quite some time. And yeah, he should actually serve as an example to many others how to actually cooperate in a security space. This is how it looks like. You just in the NoScript options, you now have an external filters tab. Where you can, you just say where the executable for Blitzableiter is. You can turn on and off the filtering for individual sites. So it's the UI flow is the same as everything else in NoScript, so it doesn't require any learning on your side. It should actually simply work. The integration into websites is also a fairly trivial thing, since it's a command line utility. You can just put it behind your upload form and check the return value. If the program exited with 0, then everything is fine. Otherwise, the file was evil. And we're considering offering a SOAP or XML RPC or whatever servers so people can use that. But we haven't built it yet, because we're actually we want to see what the feedback on this is, whether someone actually wants to use that or not. Blitzableiter is open source. It's GPL v3. The main reason behind this is because I believe that Kerckhoffs's principle from cryptography, which says that everything should be public except for the secret key, so the algorithm and everything should be open, should also apply to defense mechanisms and security mechanisms. I don't want to believe in yellow boxes that, the people promise they will make me secure and them rich, and usually it only fulfills the second requirement. I believe that if you have a security tool, you have to be put into the situation of verifying how much security it actually provides to you. Also, we want to see the code integrated into other tools that have to deal with Flash, and we love to get bug reports. The website is down here, blitzableiter.recurity.com. And there's public issue tracking. You can file bugs against us, and you can see how we perform fixing them. Yeah, so we have a demo time, which means all shit goes wrong now. Let me see. So there is my very minimal version of the internet. So let's click on a link. You see, this is what NoScript usually does, is it prevents Flash from actually happening. Now, if we choose to actually see that piece of Flash, it will load it eventually. And yeah, there it is. It's just a glass of martini. Not that I'm particularly fond of martini, but didn't find anything else. Now, if we actually use an in-the-wild implementation of a very recent exploit, we do the same thing. Please hack me. Schnupp, schnupp, schnupp. It should actually do something. I hate demos. Sorry. So what happens is, see, I'm not used to multi-monitor setups, so I didn't look at my screen. So what happens is you get a pop-up that says essentially there was a difference in the stream length from the decompression and what the header declared. So that is in the very first bytes of the Flash file. most exploits actually never bother to set the length fields correctly. And this is what happens here. So that's an in the wild exploit, and it was essentially eaten, and then you get this. Or you can configure whatever replacement file there is. You can also like flip a finger or something. This is the new function, long argument, that's relatively recent exploit that wasn't public, but I figured out how it worked and wrote one myself. That one actually has correct length fields. Now we have the same thing again. The window pops up here. So here you see that it actually, in the verifier, figured out that the index of the method is out of bounds, and so rejected the file. So much for the demo. Is anyone impressed? So, excuse me? I don't know. So this is essentially what you get. Now would be the right time to switch talks. So let's dive into the Flash format a little bit. Flash files, or so-called SWIF files, are specified from version 3 to 10. Everything is still supported. There is another quote that I like in this context: is trying to maintain backward compatibility is like trying to stay close friends with all your ex-girlfriends. We all know how well that works, and the same can be said about Flash. I mentioned that Flash can be compressed using zlib methods. There's a type length value structure thingy that they call tags. They're the main container elements. There's 63 of them defined or documented for version 10. And the data structures are extremely version dependent. So the same data structure actually looks different depending on what version the Flash file claims to be. When you look at those tag types, there's control tags that do simple things like setting the background color, or labeling stuff, or ending the Flash movie. Then there's display list tags that define and show graphic elements. You already see they're called like place object 2, place object 3. That actually doesn't mean that the second will actually place 2 objects. It's Adobe's second attempt to get it right. And then there's, the third attempt to get it right, and so on and so on and so on. They also do that with the opcodes. But of course, they still support the first version. There's bitmap tags, so you have JPEGs and BMPs and all that type of stuff. And then they have a special thing, a special graphic object they call a button. There's, again, a defined button and defined button 2. And a couple of other things. And they're used for interactive programming. So if you click on stuff, then stuff should happen. When you look at one of those tags, here's one that is called define scene and frame label data. They're often, like every tag has its own data structure. Like none of them are like close to each other. Everything is its own data structure. They're often composed of many subdata types that are then composed into lists and with counters and all types of interesting things that can very well go wrong. Very nice places for integer overflows and the like. The tag you see here to the right is actually the one that caused CVE 2007-0071. Because if you look at the scene count here, where's my mouse pointer? If you look at the scene count here, it's a 32-bit encoded number, and this one could be negative, and then it essentially overflowed. So how do we want to prevent this from happening? What we do is what I call normalization through recreation. So essentially, we parse the Flash file safely without getting owned ourselves. Then we actually throw away the original file and use all the information that we gained from the original file to create a new one. And the new one is then well formatted and can be fed into the more fragile consumer, in this case the Flash player. Very simple concept. The thing is, we have to actually implement a pretty much secure parser in order for this to be helpful. So what we did is we use managed code strictly within .NET. This allows us to define buffers and memory regions that we work on, and then have the CLR take care of whether we have out-of-bounds reads or integer overflows, which would otherwise be very, very tedious and error-prone to check manually every time. So we leave that to the CLR. We can actually load the individual TLV data blocks into individual memory streams, so every time we have an outside reference, we will catch that. And with this approach, we can also see if we have trailing data or if any of the length fields are not correct and stuff. We only accept well-documented data structures. So if there is an undocumented data structure, that we're going to reject that. The downside of that approach, of course, is that we actually have to parse everything in the file, which requires a shitload of code. If you're willing to download the source code, you will discover that it's a couple of megabytes, and that's pretty much all parser code. We also verify the version dependencies of the data structure. So if you happen to use a data structure that is only defined for version 8 and above, and your file declares to be version 6, we're going to complain about that. And here's an example why using .NET for this task is actually quite smart. In my opinion, this is what happens when you read a CVE 2007-0071 exploit. It will right here where the negative scene count, where's my mouse pointer? Where the negative scene count is, report an integer overflow exception, and then it will say reading rejected because the tag handler failed with an overflow exception. Now we're going into the Adobe virtual machines. You might have noticed already that I'm always saying virtual machines because there are two of them. It's not like it's really easy to get one right, but you can imagine how hard it is to get two right. They're called AVM 1 and 2, Adobe Virtual Machine 1 and 2. AVM 1 is historically grown. We're going to go into the history a little bit. It's a weakly typed stack machine with support for object-oriented code. It's programmed in something that's called ActionScript 1 or 2. And something around like 80% of the stuff on the internet is still AVM 1 code. AVM 2 was later introduced. It's a ECMA 262, aka JavaScript stack machine. To my extreme horror, I discovered that the ECMA specification actually only specifies the language and not the virtual machine. So the virtual machine is again completely of Adobe's making. AVM 2 is programmed in ActionScript 3, which is close to JavaScript, which is also the reason why adoption is really, really slow. Because the people that write blinky Flash stuff for internet consumption really struggle with concepts like OOP, and ActionScript 2 and ActionScript 1 are more event handler-like programming that is more natural for web developers to develop in. I want to bore you with the history of AVM 1 a little bit. Because it gives you an insight on why things are so fucked up. In the first AVM 1 introduction was in Swift version 4. Before that, there was relatively little event handler type of things that you could do. The first was already a Turing-complete stack machine. It had variables, branches, subroutine calls, everything you would wish for. Interestingly enough, they decided to have all variables being strings. So if you would add two numbers, it would actually push two string representations of the numbers onto the stack and then call the add opcode. and the add opcode will try everything in its possibility to convert the string into a number, and the other one into another number, and then add them, and then back to a string, and then push them back on a stack. In Swift version 5, they discovered that a constant pool is actually a relatively good idea. And so they introduced constant pools and objects that could have methods. In Swift version 6, they actually then discovered that if you have objects, it would be really interesting to have initialization code. So they introduced a new tag type for that. They also introduced checking of types, which they now had. So they actually have, in Swift version 6, they actually start to have numeric data types and stuff. In 7, the OOP functionality was enhanced, so the objects actually could have inheritance and extension, and they introduced exceptions because they're useful, and they introduced explicit typecasting. Version 8 never happened, and version 9 then introduced the AVM2 into the format which we're looking at right now, which is Swift version 10. Keep in mind that's all still supported. So where will we actually look for code in a Flash file? We talked about the tag types. There is a tag type called doAction that usually carries most of the AVM1 code. DoInit action is the tag type I mentioned for initialization code. But there is also other strange cases like the define button 2 tag, which contains a button record 2 structure that can carry additional button condition actions, which then carry AVM1 code. So you have a data structure with a data structure with a data structure with a little bit of code. The same also holds true for placeObject2 and placeObject3 tags. The interesting thing here is this code is actually triggered depending on how it clips. So you have two objects and they overlap each other a little bit. That's called clipping. So part of one of the object is cut away. And if that happens, the code that is actually attached to that object is executed. I would really love to know what type of drugs they had. The interesting thing is that many tools that we looked at, also many security tools, actually will only look at do action and maybe do init action for code. They will never discover code that is connected to shapes. The code itself is a variable length instruction set. There is either 1 byte instructions for simple stack operations like add, subtract, not, stuff like that, or n byte instructions with a 16-bit length field. The branches are the branch targets are byte offsets. They're assigned 16-bit offsets into the current code block or wherever. Function declarations, and this is really interesting. So function declarations are actually a bytecode. So in every sane executable format, you have an area that says this is my functions and this is where they start and where they end. In AVM1, you actually have an opcode that says, if I'm executed, everything past me, the next n or whatever bytes behind me, is going to be considered a function. Usually you would put something like that in a file format specification. So my assumption is actually the guy who was responsible for the file format specification was somewhere like on mushrooms. And then the guy who actually wrote the AVM1 stuff had to figure out something for himself. The function declarations also can be nested, or they can be anonymous functions that are executed right after their definition. When they introduced try-catch finally for exception handling, they at least stayed with their initial approach with functions and implemented an opcode again, that will, when executed, will define try-catch finally blocks. Which means we're running into a lot of weaknesses in this design. First of all, the byte offset branches allow you to jump in the middle of an instruction. Many people that have reversed x86 code that was obfuscated know this typical trick that you jump in the middle of an instruction and then the byte stream gets interpreted differently. This can be done in Flash as well. But you can also jump outside of the code block. You can, for example, jump into an MP3. That's no problem. And it will actually jump into the MP3 and try to execute code there. The signed 16-bit branch offset also prevents large branches, obviously, because you can only jump over 32K. So I was trying to figure out how Adobe actually implements that. So I took the official Flash CS4 developer environment and wrote a very long if statement, an if statement with a very large body, and compiled it. And the compiler actually emits invalid code. So when you execute that, it will actually jump as far as it can, and then everything that was in the if body below that will still get executed. The instruction length field allows hiding of additional data. Obviously, you can set a longer field than you actually need for the instruction, and then hide some data there. And there's argument arrays that you can do the same thing with. The order of code execution is extremely non-deterministic. It depends on the order of the tags and their type, on references, on some conditions to execute, like clipping, and on the visibility of objects. It's pretty weird. So what we do in a code verification, we just check all those properties. Instruction length, the number of arguments that the instruction needs, the declared instruction length, is it completely used? Does the code flow remain within the code block? Does it jump to an instruction that is actually defined, or does it jump into an instruction? Are all the addresses that are coming out of function declarations and in try-catch finally blocks actual instructions? If we do all that correctly, and I believe we do, then we end up with a nice and well-formed Flash file. And this Flash file can actually then be used to counter functional attacks that use Flash functionality instead of trying to exploit the player. Static analysis will provably not be able to determine for any given code what it actually does. That's a problem that we run into in informatics all the time. We considered emulating the code execution, but that will actually cause state discrepancies between your emulation and the actual Flash player. And that would mean that you're making wrong decisions on the functionality of the Flash code. So that's really not an option. So what we do is we do the same thing that you would do in dynamic analysis. In dynamic analysis, for example, let's say you're debugging a Windows binary or something, you will set a breakpoint right at the point in code where the function is executed, like create file. And then you will examine the arguments that are either on the stack or in registers, excuse me, for what is actually in them. Because at that point, whatever obfuscation and strange stuff might have happened before, at that point where the actual execution of the function happens, the arguments must be in place. So what we do is the same thing with Flash. The problem is we're not there when the Flash player actually executes the code. So we can't set a breakpoint within the Flash player. But what we can do is we can actually patch the Flash code in order to perform the checks that we are interested in. How does that look like? Here's an example. Action get URL2. That's again the second attempt to get the operation get URL right. Is the most widely used function or bytecode to actually forward the browser to another URL. When we handle the Flash file, we know where it came from, so we can actually introduce a more strict same origin policy test than the Flash player will actually do. And this is how that looks like. Here's a code flow graph of a original file. And in the block with the ID 31, you see that there is an action get URL, which gets some arguments. In this case, it's constants, but it could be anything. It could be somewhat pre-computed that we couldn't determine. up front. So what we can do is we just introduce another 2 blocks that will actually do a string comparison on the URL that we got the flash file from. In this case, it's dougal.com. And if those equal, then we do execute the get URL2. And if not, we just clean up the stack and go on. So nothing happened. This gets more interesting when you try to capture arguments of object methods. I'm not going into all the detail of those code blocks here, but essentially what AVM1 usually does to call a method on an object is first loading the variable by name, and then actually pushing the method name and then calling the method. So you need the code over there to actually figure out if the respective method of a object is called. It gets even worse. If you decide to not have that call happening, this is all the code you need to clean up the stack of the stack machine when you didn't actually execute the function or the method of the object. And you see that this is quite a lot of code. And when you put that into every place where a method of an object is called, you get quite some inflation. That's what you see here. On the left side, the one that's completely blue, is the complete code flow graph of the Gnida malware example. On the right-hand side, you see the same code flow graph, and with the little red thingies, that's the basic blocks that we introduced. And you can easily see that we have quite some code inflation here, approximately 250% of the original code. However, every single method call and every single call to an instruction that has anything to do with forwarding your browser to a new URL is actually covered now. So the code is secure, but it's, in my eyes, it's a little bit too big. So what we do to prevent patches on places where we can actually prove that the argument is a constant that fulfills a certain requirement that we have, we can determine those things using backtracing of the virtual machine stack in the code flow. So we build a code flow graph. If we find an instruction that interests us, we do backtracing and try to figure out what the state of the stack is at any given point. The problem is we always need code flow graphs, even if it's a load from the constant pool, because brilliantly enough, the defined constant pool is also an instruction. So within the instruction stream, you can totally overwrite your constant pool. And so we actually have to know in what the code flow is in order to figure out which constant pool is currently used. The goal for the higher level verification model is that we can actually say, like, for an object, for a method, the second or third argument, does it fulfill the following requirement, which is usually a string comparison. So the way we implement that right now is we have our own virtual machine, stack machine. It's actually two. Which gets executed, and it has instructions that are of very small granularity, like get the third argument or argument number n of this instruction, and it will try using static analysis to get to that point to figure out that argument. If it somewhat fails in the execution, so it runs into an undecidable situation regarding the stack state, it stops execution. And we run the same virtual machine again in a different mode where it doesn't actually do static analysis, but actually emits the AVM1 code that will do the same functionality. In this way, we can actually keep the individual functions very small, and we can ensure that the static analysis step and the AVM1 code that we emit are functionally equal, because otherwise we run into situations where those two diverge, and then we can get owned. Very recently, we introduced AVM2 support, the second Adobe virtual machine. So the tool that we released today actually does support both virtual machines now. The AVM2 is design-wise a lot closer to the AVM1 than it should be. What I'm trying to say is it's also fucked. They fixed a couple of things, so we actually only have one constant pool now, and functions and methods are actually defined in the file format. It's interesting because the ABC format that they use is a complete file format that goes into this one tag type. It looks a little bit like the Java class file format, actually. Stack tracing for AVM2 isn't there yet. The aim is to have the higher level verification that I was just talking about, being a unified layer over both virtual machines, so you don't have to care about that. There is an interesting tidbit about the specification for ABC. Someone who wrote the specification actually wasn't so stupid, because that person said, well, all the length fields we have in a specification are 30-bit, not 32. Why is that smart? Because if you have one good spec designer, like this guy, he can actually prevent all your bad coders from having integer overflows. Because if you add two 30-bit integers, you still don't overflow your integer. Of course, if you multiply them, then game is over. So that was actually really smart. The interesting thing is, if you look into Tamarind, which is the open source implementation of AVM2, which apparently, according to Adobe, is essentially what AVM2 state-of-the-art is. This is the function that reads those 30-bit integers. And if I may point to the last 3 lines, you will actually see that it parses out 32-bit. As much as I respect the spec designer for his idea, the basic parsing function within the code of the company that came up with this actually already fails that specification. So what happens when we use Blitzableiter in the real world? So far, we haven't found a single exploit that would actually pass through the format normalization layer. As I said in the demo, most exploits actually don't even bother to set the length fields correctly, which speaks volumes of the Adobe parser, because that actually doesn't care about the length fields too much. And they are all caught by the format verification and normalization. Recent exploits, as I mentioned, have been caught by the code. We have been eating our own dog food as you should, and we're so far happy with it. So YouPorn works, YouTube works, so do many other sites. Just in case that we severely fucked up something in the code, you can turn off individual tag handlers in a configuration file, which then says that this tag is verbatim copied over as a byte array instead of parsed and normalized. Flash files that have code obfuscation, they usually use jumps into instructions and all that stuff that I was mentioning before. They get rejected, obviously, because the code is not well-formed. That affects a couple of sites like Hulu.com, which tries to prevent people outside of the United States to use their service. Many third-party Flash generators emit invalid Flash files. They use undocumented tag types, reserved fields, or ridiculously broken Flash for whatever reason, because the parser is so forgiving that you can actually create a lot of crap and it will still display something. So that is one of the bigger issues that we have is compatibility. So we want to make sure that the user experience is still acceptable, so not too many things get rejected. For that, we actually need the feedback of the community that hopefully uses it, like all 3 people of them. This is why the dialog box you've seen in the demo actually has a button that says like report this as invalid. So we can actually look at the Flash file that was eaten by Blitzableiter, and if you're convinced it's a good file, then you should actually press that button. Keep in mind that like many non-malicious Flash files are nevertheless really malformed and should be actually filtered because they're against their specification. Case in point here is half of the samples on Adobe's DevNet site, like the site that is actually supposed to show you the features of Flash, half of them actually violate their own specification. They make use of exception handlers that they do not declare. No idea how they produce those files, but it again speaks volumes. We only, like when you report something to us, we only store the content in the log file. It's all HTTP, so if you don't believe me, just sniff it yourself. And we also want to know if a Flash file sounds or looks different after it was filtered, because that is something we cannot automatically test for. And also, if something like that happens to you, then please let us know. So, brings me to the conclusions. We think that Blitzableiter shows that you can produce signature-free protections. They do have the burden of the initial implementation being hard and complex, but once you're over that, you can actually leverage the managed language environments and parsers to create format normalization. And I personally think that this approach can also be applied to other file formats. Things that are parsed by programs from the same vendor come to mind because they're often used for exploitation. Automated code property verification and enforcement is an interesting way for Flash content distributors to enforce contractual regulations and requirements. Not surprisingly, as you probably notice, it's a bit of a tricky area, but it can be done, and it is, in my eyes, a very valuable tool for people that have to accept content from third parties. And we simply hope that this tool is going to be a useful addition to your browser protection measures and allows you to surf your porn more safely. Here's some acknowledgement. Robert Hetzler is one of our interns. He works on this project, and he pulled quite some handful of hairs out during the attempt to parse that stuff. And Dirk Bryden is one of my teammates and helps me get something like this done. Mumbi is just generally awesome. And by the way, DJs tonight at B-Sides. So if you like good electronic music, then you should show up there. And that was it. If I still have time, I'm open for questions. Do I have time? I do, yeah. And I'm sorry that you missed Dino's talk. So anyone, any questions? I don't even... What was that? There's a mic coming to you.
How do you handle SWICs and third-party controls?
What do you mean with third-party controls?
You can actually embed SWC objects into the Swift file format and actually execute those codes as part of your program. Also, it's like using Acme.
Okay. I'm not 100% positive what you're talking about. We should actually, can you point me at the part in the spec that allows this?
Yes. Okay.
Well, if it's in the spec, it's handled. Like, we're really handling the complete SWF10 specification. If it's bytecode, then it gets automatically handled by the bytecode verifiers. But are you saying it's not bytecode?
Like Pixel Bender is also a plugin that is in Flash. There's also a SWIC, third-party compiled codes.
Yeah, but it's still compiled code.
Yeah, it was from C to bytecode converted.
Yeah, but it's still AVM code then.
you can run AVM1 inside of AVM3.
Well, we don't have an AVM3 to begin with.
Or, sorry, AVM2.
Well, this is interesting. So we do handle those cases, although Adobe actually says it's impossible that you can run both virtual machines at the same time.
Right.
But I have seen cases that this works. So we actually don't. So the Flash player actually makes a decision which virtual machine to instantiate based on the file attributes tag when loading the Swift file. It runs on the assumption that you're actually only having one virtual machine at the time, and we're not sharing that assumption. Like if you have AVM1 and AVM2 code, we will actually verify both.
This came off the Alchemy research from their site, Alchemy?
Mm-hmm.
Okay. Which was using the Swix and the Pixel Bender.
Well, if in doubt, then just try it out and let us know if it just explodes in your face or does what it's supposed to do.
Okay.
That's the whole point of releasing that tool as a browser add-on. Is like there's so many weirdnesses in the Flash world that we can't possibly know about all of them. So that's why we're asking other people to try this. Any other questions? Do we have contact with Adobe? Yes, we do. They're actually surprisingly open to the whole idea, and we're trying to get to a point where we can discuss, especially cases where the specification diverts from the reality on the internet, and would like the samples on their own example page. And we're trying to engage them into discussions on like what are we supposed to do in this case. So let's see how that develops. The talks with Adobe are relatively new. They just happened like yesterday or 2 days ago. Let's see if they actually like put the actions where the talk is right now. But I'm relatively positive that we can at least engage them into specification side discussions. No more questions? Okay, thank you.